We present SLCF-Net, sequential LiDAR camera fusion for semantic scene completion using a 3D recurrent U-Net. Our approach aims to simultaneously estimate the complete geometry and semantics of a scene from an RGB image and the corresponding sparse LiDAR depth map. In the feature extraction part, we employ the 2D U-Net to extract semantics from the RGB image and design a depth-conditioned pipeline fueled by depth anything to predict the dense depth priors. Afterward, the GDP module backprojects the 2D features into a predefined 3D volume using the depth priors. The 3D features are then fed into a 3D U-Net, which produces a dense semantic scene. Notably, this 3D U-Net keeps hidden features, allowing it to learn information from the previous frame. Two highlights of this framework are the GDP module, which projects 2D features to 3D space, and a 3D recurrent U-Net, which learns temporal information. Let's start with the GDP module. A 2D feature located at pixel P can be backprojected along the line of sight. All the voxels passed by the line of sight can be related to this feature. With the depth prior, the p-hat is considered the most probable point, and the weight is decayed with the increased distance to the p-hat. We describe this weight with a Gaussian decay function. To utilize the information from the previous frame, we design a 3D recurrent U-Net. There's an overlap area between neighboring frames. With the known pose of each frame, we propagate the features in the same global positions via coordinate transformation. Parts of the scene in both the estimation and the ground truth lie outside the field of view, which are visualized as shadow areas. The unknown regions, as defined by the ground truth, are visualized at 20% opacity. We compared our approach with other state-of-the-arts. The SLCF-Net outperforms the leading SSC metrics. In summary, the main contributions of this paper include: Introduction of SLCF-Net, a novel SSC method that fuses 2.5D sparse depth maps with 2D RGB images, adaptable to various sensor configurations. The GDP module, a Gaussian-decay Depth-prior Projection method for projecting 2D features into 3D, a mechanism that propagates features from the previous frame to the current frame based on the known coordinate transformation. Thanks for watching.